Hello and welcome to a new video on IGCSE Physics Classified Paper 4. In this video, we shall be discussing the topic of momentum. So we are required to state the word equation that defines momentum. Momentum is equal to the mass times the velocity of an object. So mass times velocity would work for question 1. In question 2, we are required to underline a pair of quantities which must be multiplied together to calculate impulse. So impulse is the change in momentum, and it is equal to force and time. So force multiplied by time, I equals F times T. This gives us the impulse. In the third question, we are required to define impulse. Like we said, impulse is the change in momentum, or it is the force multiplied by time. These are two different definitions, both of which are correct in defining impulse. State an expression for the kinetic energy of an object of mass m that is moving with a speed v. So you should know that the kinetic energy of an object is half mv squared. State and explain whether kinetic energy is a scalar quantity or a vector quantity. Kinetic energy is a scalar quantity since it has no direction. The velocity of an object of mass m increases from u to v. State in terms of mu and v the change of momentum of the object. So the momentum of an object is mass times velocity. So final momentum would be mass times final velocity. Initial momentum would be mass times initial velocity. Therefore, the change in momentum would simply be final minus initial. That's why we have mv minus mu as the impulse or the change in momentum of the object. In the third question here, we're required to complete the table by writing in the right-hand column the name of the quantity given by the product in the left-hand column. So if we have mass times acceleration, you should know that F equals ma. So therefore, the quantity here is force. If we have force times time, this gives us impulse. So impulse is equal to force times time. Sometime later, the rocket is far from the Earth. This is a separate question. It is part of a larger question, but we are only interested in question C, which has to do with momentum. So it says sometime later, the rocket is far from the Earth. The effect of the Earth's gravity on the motion of the rocket is insignificant. As the rocket accelerates, its momentum increases. State the principle of the conservation of momentum. So the idea that momentum is conserved, of course, this is the principle of conservation of momentum, but you cannot just say momentum is conserved. You have to say that as long as there are no external forces affecting the system. So it has to be what we call a closed system. In a closed system, momentum is conserved. What do we mean by a closed system? We mean that two bodies are just colliding together. There are no extra forces. There are no additional outside forces that affect the system. So in the absence of external forces, this is a key word here, momentum is conserved. Explain how the principle of conservation of momentum applies to the accelerating rocket and the exhaust gases. So the increase in momentum in the exhaust gas is equal and opposite to the increase in momentum of the rocket as it travels. In other words, the rocket, excuse my bad drawing, but the rocket is traveling upwards and its momentum is increasing because it's accelerating. This is balanced by more and more gas being emitted downwards, such that the momentum of the gas has to equal the momentum of the rocket, so that the total momentum of the system is conserved. In other words, the change in momentum of the rocket, the increase in momentum of the rocket, has to equal the increase in momentum of the gas, equal and opposite in direction. Figure 2.1 shows a dummy of mass 70 kilograms used in a crash test to investigate the safety of a new car. The car approaches a solid barrier at 20 meters per second. It crashes into the barrier and stops suddenly. calculate the momentum of the dummy immediately before the crash. So like we said, momentum is mass times velocity. So all we have to do here is multiply the given mass by the given velocity, and we get the momentum as 1,400 kilograms meters per second. Determine the impulse that must be applied to the dummy to bring it to rest. I want to draw your attention to the verb that they used in double I. So in I, they said calculate. So we had to actually perform a calculation. However, in double I, they just asked us to determine. And by determining, that means that there are no further calculations required. You just need to use your common sense to understand that since the momentum is 1,400, in order to bring it to rest, where the momentum is going to be 0, all you have to do is decrease the momentum by 1,400 as well. So the idea is that you understand that if you have a momentum of 1,400, you need an impulse of 1,400 to come to rest. So in B, we are told in the crash test, the passenger compartment comes to rest in 0.2 seconds. Calculate the deceleration of the passenger compartment. So you can use multiple techniques here. I just decided to use equations of motion because we know that the final velocity is 0 and the initial velocity is 20. So we can use u as 20. And we want to get the acceleration knowing that the time is 0.2. So we're just going to solve for A. So A, we have here V equals U plus AT like this. 0 equals 20 plus 0.2A. You take the 20 to the other side, you get negative 20 equals 0.2A. And then A equals negative 20 over 0.2, which gives us A equals to negative 100. Negative 100 means that the deceleration is 100 meters per second squared. In C, we're told the seat belt and airbag bring the dummy to rest so that it does not hit the windscreen. The dummy has an average deceleration of 80 meters per second squared. Calculate the average resultant force applied to the dummy of mass 70. All you have to do here is just multiply the mass, by the acceleration. So MA gives us F, and you can get F simply by multiplying the two quantities. It doesn't matter whether it's acceleration or deceleration. This just means that the net force or the resultant force is applied backwards because the object is decelerating. But the same rule applies. F equals MA, which just get us the value required. In D, we are told the deceleration of the dummy is less than the deceleration of the passenger compartment. Explain why this is of benefit for the safety of a passenger. So why do we want the deceleration to be smaller? Because this means that the net force applied is smaller since F equals MA. So if the deceleration decreases, then the force decreases. And if we have less force, this means that there is less injury. The whole point of all of this is to minimize or prevent injury during the collision of cars. So in order to do that, in order to minimize that, you want to decrease the deceleration so that the force applied decreases as well. Figure 2.1 shows two railway trucks on a track. Truck A of mass 6,000 is moving at 5. It is approaching truck B of mass 5,000, which is stationary. Calculate the momentum of truck A. So of course, the momentum of truck A is simply the mass of truck A times the speed of truck A. So this is quite simple. We multiply these two quantities together and we get 30,000. The trucks collide, their buffers compress, and then they bounce off each other, remaining undamaged. After the collision, truck B has a momentum of 27,000 kilograms meters per second. Determine the impulse applied to truck B. Like we said in the previous problem, the verbs are very indicative. So calculate means that you're actually going to perform a calculation. However, determine means that there is no calculation required. You are simply going to use common sense to figure out what the impulse is. So B was initially at rest. And so B is stationary, which means it's at rest. So the initial momentum of B is 0. And then the final momentum is 27,000. So what's the impulse? It's the change in momentum. So it's equal to 27,000 as well. The trucks are in contact for 0.6 seconds. Calculate the average force. So now that we have the impulse, we can use the rule I equals Ft. But since we want the force, we can change it into F equals I over T. And impulse over time gives us 27,000 divided 0.6, which is 45,000. Calculate the final speed of truck A. So in order to calculate the final speed of truck A, there is a systematic way, which I've done here, and there is a conceptual way. I will explain both. I will just explain the conceptual first since it's shorter. The idea is that momentum is conserved. So you have truck A and you have truck B. So we are told that B was initially 0 and the momentum increased by 27,000. Because we said that the impulse is 27,000 and that the momentum, of course, increased since B was initially at rest. So that tells us that for A, the momentum must decrease by 27,000 as well, since the total change in momentum is conserved. Now, since the momentum was initially 30,000, this tells us that the final momentum of A is 30,000 minus 27,000, and that tells us that the final momentum is 3,000. And this is equal to mv. So if we divide 3,000 by the mass, v gets 3,000 divided by the mass of A, which is 6,000. And then if we divide those, we get 0.5. And this is the correct final answer. So the way I explained on the screen was more conceptual, less systematic. There is a systematic way by simply writing down the equation m1u1 plus m2u2 equals m1v1 plus m2v2. And you plug in all the quantities that you're given. Of course, you know that mass 1 is 6,000, and this is the same before and after collision. So this is 6,000, and this is 6,000 as well. Now, u1 is the speed of A before the collision, and that is 5. That is given in the problem as 5. There it is. And then we know that B is stationary before the collision, so this is all going to be 0 anyway. And then we want the final speed of A after the collision. We don't know the final speed of B, but we do know that mv in general is equal to 27,000. This is the final momentum of B. So we take this 27,000 and we put it here as one single entity representing m2v2 as a whole. So m2v2 as a single unit is equal to 27,000. And then we have an equation with one unknown, and we can solve for v1, getting the same answer that we got the first time as well. A footballer kicks a ball vertically upwards. Initially, the ball is stationary. His boot is in contact with the ball for 0.05 seconds. The average resultant force is 180, and the ball leaves his foot at 20. Determine the impulse. So impulse is force times time. We are given the force, which is 180, and the time, which is 0.05, and we get the impulse as 9. Determine the mass of the ball. Of course, impulse is mass times velocity. Now, we already have the impulse as 9. We got that in A. And then the velocity is 20, and we want to get the mass. So the mass is going to be 9 divided by 20, which is 0.45 kilograms. Next, we're required to find the height to which the ball rises. I like to use the equations of motion to solve this kind of problem. Of course, you could have used an energy method as well. You could have used kinetic and potential energies. This would have also worked. But I like to use the 4 equations of motion. Let me write them down and make a note of them. They will simplify life for you in mechanics. So we have V equals U plus AT. V squared equals U squared plus 2AS. S equals UT plus half AT squared. And S equals U plus V over 2 multiplied by T. Now, in this case, we want the height to which the ball rises, ignoring air resistance. So the height is S. And since that this is the maximum height, we know that the speed must be 0. And the acceleration due to gravity is -10. And of course, the initial speed is 20. This is already given. And we use v squared equals u squared plus 2as. And we solve for s. So 0 equals 400 plus 2 times -10 times s. 400 minus 20s equals 0. And s equals to 20. In B, we are told, while the boot is in contact with the ball is no longer spherical. State the words used to describe the energy stored in the ball. This is called elastic potential energy or strain energy. This is the energy stored in the ball while it is momentarily changing in shape as the footballer kicks it. So it compresses momentarily and it has elastic potential energy, and then it is restored to its original shape and moves up. In this question, we're told figure 3.1 shows a collision between two blocks, A and B, on a smooth horizontal surface. And we are given some information. We want to calculate the momentum of A before the collision. Of course, we are given the mass and the speed, so we just multiply them together, and we can get the momentum here quite easily. 2.4 times 3 equals 7.2. Then we want to get the velocity V, which is the velocity of the two bodies as they move after the collision. So we apply the momentum equation, m1u1 plus m2u2 equals m1v1 plus m2v2. And we plug in each value at a time. So we have A has a mass of 2.4. So this is 2.4 and this is also 2.4. B has a mass of 1.2. So we plug the same mass here and there. B is initially at rest, so the speed is 0 initially, and the speed of A initially is 3. After collision, they stick together, which tells us that they have the same speed. So therefore, we can rewrite the equation as 2.4 times 3 plus 0 equals 2.4 V plus 1.2 V, which tells us that 7.2 equals 3.6 V, and we can get V as 2. Now we want the impulse experienced by block B during the collision. Now, if we can get the final momentum of B, we can get the impulse because this is 0 and this is the final momentum. So if we can just get the final momentum, the impulse is the same as the final momentum since the initial momentum is 0. So therefore, the impulse is going to be 1.2 times V, and we said that V is equal to 2, so the answer is 2.4. Suggest why the total kinetic energy of blocks A and B after the collision is less than the kinetic energy of block A before the collision. Because during the collision, you have noise, you have sound energy, and thermal energy. So you have some of the initial kinetic energy is transformed into heat and sound. Figure 2.1 shows two cars, A and B, before they collide. Car B of mass 1,200 is stationary. Car A of mass 2,000 is traveling towards car B at 18 meters per second. Calculate the momentum of car A. So the momentum of car A is equal to the mass times the velocity. And the mass is 2,000 and the velocity is 18. So we get 36,000 kilograms meters per second. In B, we are told the cars collide and car B experiences an impulse. Car A continues to move in the same direction with a momentum of 21,000. Calculate the momentum of car B immediately after the collision. So we begin by writing down the momentum equation. m1u1 plus m2u2 equals m1v1 plus m2v2. Of course, the masses are given. And the momentum of A, of course, is 36,000. So the momentum of A before the collision was already calculated. The momentum of B is 0. And then the momentum of A after the collision is given as 21,000. So we write that here instead of m1v1. And we want to get m2v2. So we can simply subtract 36,000 minus 21,000 and we get the momentum of B. In other words, you can think about it as follows. The total momentum before the collision is 36,000 because the momentum of B is 0. And then after the collision, B has 21,000. So what does A have? Or A has 21,000. So what does B have? So the 36,000 given before the collision are distributed among A and B. If A has 21,000, then B must have 15,000 so as to complete the initial 36,000 because we said that momentum is conserved. Now, since B was initially at rest, the impulse is equal to the final momentum, which is 15,000, again, kilograms meters per second. Now that we have the impulse, we are required to get the force. We know that impulse is equal to force times time, and we are given the time. So all we have to do is divide the impulse by the time, 15,000 over 0.2, and we get the required force. In C, we are told a modern car is designed so that during the collision, the front section of the car is crushed and the time of contact increases. Explain the benefit of increasing the time of contact for the people in the car. The benefit comes from this equation here. If we increase the time of contact, meaning that we increase this value here, then the force will decrease. So the average force is going to decrease. And instead of 75,000, for example, we're going to get a smaller value. So therefore, longer time means smaller force on the passengers. And the whole objective is to reduce the force on the passengers so as to reduce injuries in case of accidents. A metal block A traveling in a straight line at 4 collides with a second metal block B, which is at rest. The figure shows two metal blocks A and B before and after the collision. The mass of A is 3.2 and the mass of B is 1.6. After the collision, the velocity of A is 1.5. Calculate the momentum of A before and the velocity of B after. So the momentum of A before the collision, this is quite simple. We have to multiply the mass by the speed. 3.2 and 4 are already given before the collision here. Of course, this gives us 12.8 or approximately 13 kilograms meters per second. Next, we want the velocity of B after the collision. So we use the momentum equation here. M1 U1 plus M2 U2 equals M1 V1 plus M2 V2. The initial momentum of B is 0 because it's at rest. And we solve for the velocity of B after the collision. Since we're given everything else, we're given the velocity of A after the collision as well. So we just plug in the values. So 3.2 is the mass of A, and 1.6 is the mass of B. 4 is the initial speed of A, and that's given. And 1.5 is the final speed of A, and that's given as well. So all we need to do is just plug in the values, and we solve for V. We get this equation here, and we solve it for V, and V is equal to 5 meters per second. In the collision, block A and B are in contact for 0.05 seconds. Calculate the average force. Again, we want the impulse over time to get the force. Since we have the final momentum of B, the final momentum of B, of course, is 8 because it's 1.6 times V. So if you multiply 1.6 times 5, you get 8. So 8 divided by the given time, and that gives us the given force. You can see that the questions are repeating. It's the same idea, just with different numbers. And in D, we are told again that the total kinetic energy after is less than the total kinetic energy before. And the reason for this is that energy is lost as heat and sound. It seems that we are repeating ourselves again in this question. Figure 2.1 shows two fairground bumper cars. The car with passengers of total mass 200 is moving in a straight line. It is traveling at 2.5 when it hits a stationary empty car of mass 50. After the collision, the empty car moves forward in the same direction at a speed of 4. For the car with the passengers, determine the momentum while it's traveling at 2.5. So we're given the mass and we're given the speed and asked to calculate the momentum. And then in double I, we are required to find the speed and direction of the motion immediately after the collision. So we use the momentum equation here. M1 is given as 200. M2 is given as 50. The momentum of B before is 0 because it's at rest. The speed of A is 2.5 before, and we want to get the speed after, knowing that the speed of B after the collision is 4. And this is given here that the empty core moves forward at the speed of 4. Now we make our appropriate calculations. 200 times 2.5 is 500. And on the right-hand side, we have 200 V1 plus 200. And we can calculate V1. It turns out to be 1.5 meters per second. And of course, since it's positive, we have to write that it is same as the original direction of motion. In triple I, we are told fixed to the front and back of the cars are large springs. When the cars collide, the springs compress. The total kinetic energy before is equal to the total kinetic energy after. Describe the energy transfers that occur as the cars collide and then separate. So the kinetic energy of the cars is converted to elastic potential energy as the cars collide and the springs compress. And then this is converted back to kinetic energy when they separate. So you have kinetic energy initially, and then when these springs collide, they compress and they have a lot of stored elastic potential energy. And then when they leave each other again, the elastic potential energy is converted back to kinetic energy. In a game of tennis, a player hits a stationary ball with his racket. The racket is in contact with the ball for 6 meters per second. The average force on the ball during this time is 400. Calculate the impulse. So the impulse is force times time, and we're given both force and time. But of course, here we have to convert this to seconds. So we divide it by 1,000, and we get the impulse as 2.4. In double I, we're told the mass is 0.056. Calculate the speed with which the ball leaves the racket. So the ball is initially stationary, so it has 0 speed initially. And we are given that the impulse is 2.4. So impulse is final momentum minus initial momentum. 2.4 equals the mass times the speed minus the initial momentum, which is 0 because the ball is stationary. And we want the final speed. So now we have an equation in V. We divide 2.4 by 0.056 and we get 42.9. Of course, this is approximately 43. State the energy transfer that takes place as the ball changes shape during contact between the racket and the ball. So we solved something similar to this, but with football. When the footballer kicks the ball, we said temporarily the shape changes and it has elastic potential energy or strain energy. And then as the ball leaves the racket, the strain energy is converted into kinetic energy again. So the kinetic energy of the racket gives the ball strain energy, stored elastic potential energy. And then as the ball leaves the racket, the strain energy is converted back into kinetic energy. This figure shows a man hitting a ball with a golf club. The ball has a mass of 0.046. The golf club is in contact with the ball for 5 times 10 to the power of -4 seconds, and the ball leaves the golf club at a speed of 65. Calculate the momentum of the ball as it leaves the golf club. So the momentum of the ball is mass times velocity. We are given the mass here, 0.046, and we are given the velocity as well. So we multiply them and we get the momentum. Now we want the average resultant force. Again, here the ball is initially, excuse me, the ball is initially stationary here. So therefore, the impulse is the same as the final momentum. So therefore, the final momentum is written here instead of the impulse, and we divide it by the given time in order to get the force. So the force is approximately 6,000 newtons. While the golf club is in contact with the ball becomes compressed and changes shape. State the type of energy stored in the ball during its contact with the golf club. We said this before, it's called strain energy or elastic potential energy. Figure 2.1 shows a model fire engine. Its brakes are applied. 0.8 kilograms of water is emitted in the jet every 6 seconds at a velocity of 0.72 relative to the model. calculate the change of momentum in the water that is ejected in 6 seconds. So the change in momentum is equal to mass times velocity, and we have the mass as 0.8 and the velocity as 0.72. So we multiply them together and we get the impulse as 0.576 or 0.58 approximately. Next, they want us to calculate the force, so we divide our result here or there by the time, which is 6 seconds, and we get the magnitude of the force. And then we have some conceptual questions to solve. We are told the brakes of the model are released. State and explain the direction of the acceleration of the model. So if there are no brakes, if the brakes are released and the model is ejecting water very strongly in this direction, where would the car move? So it's called recoil, similar to when you fire a gunshot and the rifle moves backwards or the gun moves backwards. This is called recoil speed. So since the water is moving in this direction, the car itself is going to accelerate in this direction. It might move, it might not, but either way, the acceleration is going to be to the right. So why will it accelerate to the right? It must be equal, it must have an equal in magnitude but opposite in direction momentum to the water. So the resulting force must be to the right. D says, in C, the model contains a water tank which is initially full. State and explain any change in the magnitude of the initial acceleration if the brakes are first released when the tank is nearly empty. So again, here the momentum is the same. However, the mass is going to decrease. So since we have the same force, but less mass, therefore we have greater acceleration. So the idea here is to understand that F is constant and M decreases, so A must increase opposite to M. Figure 2.1 is the top view of a small ship of mass 1.2 times 10 power 6. The ship is moving slowly sideways at 0.04 as it comes into dock. The ship hits the wooden pillars which move towards the dock wall. Calculate the kinetic energy of the ship before it hits the pillars. So we multiply half by m by v squared, and we are given everything here. We have the mass and we have the speed. So we multiply half times mass times speed squared, and we get 960 joules. In B, we are told the ship is in contact for 0.3 seconds. Calculate the average force. Again, if we have time and we want force, we probably need to use impulse equals force times time, but we rewrite it to suit force. So force is equal to impulse over time. So therefore, we have impulse over time, and time is given as 0.3. Impulse will be the final momentum again, or the change in momentum, which is 1.2 times 10 power 6 times 0.04. Since it's going to come to rest, so the final momentum, in fact, is going to be 0. We want the initial momentum minus 0, so therefore we just put in the initial momentum of the ship. And therefore, 1.2 times 10 power 6 times 0.04 divided by 0.3 gives us 160,000 newtons, which is almost 1.6 times 10 to the power of 5 newtons as well. Assume that the kinetic energy calculated in A is used to do work moving the pillars. Calculate the distance moved by the pillars. So here, this is a work question. Work equals force times distance. And we are given that we want the distance. So distance is equal to work over force. We have the force already, and we have the work since it's equal to the energy. So we simply divide 960 by 160,000, and we get the distance as 0.006 meters. Dock walls sometimes have the pillars replaced with rubber car tires. Explain how this reduces the possibility of damage when a boat docks. Because rubber has this ability to absorb shock in a sense. It increases the time of the collision. It changes shape to absorb the shock, so it increases the time. And like we said in previous problems, if the time increases, then the force decreases for the same impulse. So if we have the same collision and we have the same collision occurring twice and one of them occurs in longer time, it will result in a smaller force, of course. Figure 2.1 shows a train. The total mass of the train and its passengers is 750,000. The train is traveling at a speed of 84. The driver applies the brakes and the train takes 80 seconds to slow down to a speed of 42. Calculate the impulse applied to the train as it slows down. Of course, we have the mass and the final velocity and the initial velocity. So we can just do mv minus mu, and that suffices to get the impulse here. Calculate the average resultant force applied to the train as it slows down. We simply divide impulse by time. We got the impulse here, and we are given the time in the problem, 80 seconds. So therefore, we divide impulse by time, and we get the force as 3.9 times 10 power 5. Suggest how the shape of the train helps it to travel at high speeds. So the idea is that the shape helps to reduce air resistance in order to maintain high speeds. It is called a streamlined shape. This is called a streamlined shape. You don't have to write the word streamline, but the idea is that the streamlined shape of the train helps to reduce air resistance. In D, the train took 80 seconds to reduce the speed from 84 to 42. Explain why, with the same braking force, the train takes more than 80 seconds to reduce from 42 to 0. So this is nice. This is a conceptual question. They are saying that we have the same braking force, and to go from 84 to 42, it took us 80 seconds. But to go from 42 to 0, it takes more than 80 seconds. So for example, it takes 90 seconds or 100 seconds or whatever. So why would that be the case, even though the change in both cases is minus 42? Why would this case take more time, even though the same braking power is applied? So the idea is that the train is opposed by two forces, braking power and air resistance. So braking power is the same. However, when we're going from 84 to 42, this is a very high speed on average. So you have a lot of air resistance. You have high air resistance. But from 42 to 0, you have a smaller air resistance on average because the speeds themselves are, the average speed from 42 to 0 is much smaller than the average speed from 84 to 42. So therefore, in the latter case, the air resistance will be smaller and it takes more time to reduce the speed. So even though the braking force is the same in both cases, the air resistance plays a more significant role with the higher speeds. On a wet day, the train travels a greater distance before it stops along the same track. The train has the same speed of 84 before the brakes are applied. Suggest a reason for this. This is because the friction with the ground is reduced by the rain or the wet day. So therefore, the friction force decreases when the brakes are applied. Figure 3.1 shows a shooting competition where air rifles fire soft metal pellets at distant targets. When an air rifle is fired, it exerts an impulse of 0.019 Newton seconds on the pellet. The pellet has a mass of 1.1 times 10 power negative 4. Determine the speed with which the pellet leaves the rifle. So of course here, this is simple enough. You have the impulse. The impulse is 0.019. And you have the mass and you want to get the speed. So why is the impulse equal to mv? Because the initial momentum is 0. So the impulse is equal to the final moment. Whenever the initial momentum is 0, the impulse is equal to the final moment. So therefore, 0.019 is equal to mass times velocity. So you divide this number by this number and you get the velocity immediately. Next, we want to get the kinetic energy, and the kinetic energy is half mv squared. We have the m and we have the v. We multiply them by each other, and we get the kinetic energy of the pellet, which is 1.6 joules. And this wraps up the question. This also brings us to the end of our video. I hope this was beneficial. Thank you for watching.